mask the conflict of interest. Okay, well, happy to have Stefano tell us about gravitational path integral from an observer's point of view.
Thank you, Edwin. So today we'll be talking about, thank you for coming to the talk. I'll be talking about this work with Ahmed and Luca and Adam that came out earlier this month. And this paper is a little bit long and technical, so my goal for the talk is to first of all give you an overview of why we're doing this, what are the motivations, what's our goal, what's our proposal, and what are our results. And then we'll go into a little bit more detail. I am not a big fan of extremely technical talks, so I'll give you a sense of what the calculations are about and what are the results, and then feel free to ask any of us later for any detail that you might want. So let's start with the motivation. So holography and the gravitational path integral are two very powerful tools that in the last few years give us a lot of very interesting results in quantum gravity. But most of their power is when you're trying to compute some global observable. And by global, for example, you can think of it as a boundary observable in the SFT. And they are sometimes a little bit less powerful when you try to compute what a bulk observer that lives in the gravitating space-time would see, at least at the current stage. So some examples of where this becomes clear is when you try to describe physics for an observer living in a space-time that, for example, doesn't have a holographic description. This includes the Sitter, cosmology, of course, closed universes, and so on. Or when the observer dynamics is in some sense decoupled by the dynamics of the boundary. One example of that, let me give you a few examples of this. So for a closed universe, for example, you don't have a dual theory, or at least not a no one. And the gravitational path integral would suggest or tells you that at the non-perturbability level, the Hilbert space is one-dimensional. And this is in contrast with the fact that an observer in a closed universe should see non-trivial physics. And we might as well be living in one. So there should be a sense in which we can make sense of this physics in a closed universe. Another clear example is an unfolding observer, where once the observer crosses the horizon, there are a bunch of questions that are still very unanswered. One of them is firewalls, that has had a recent resurgence, I would say. And also the problems of dependence, which we know that in some regime we can still describe the semi-classical physics of this observer, but on the other hand, the fact that the reconstruction is state-dependent, if you go, for example, at very late times, suggests that there is some ambiguity in the experience of these observers in the interior. And finally, I put this here because it reminds me of the common horses story that Raphael talks about, and it's the idea that if you have a single weird patch, which is encoded in a single time slice of a period space-time, you can cook up situations in which the experience of an observer moving within this weird patch is ambiguous. I won't go into any detail of that because it won't be relevant for this, but I think this enters in this class of cases in which the experience of a bulk observer is not very clear how you can reconstruct it from a dual theory or using the gravitational method.
So can you really clarify the last one a little bit more?
On the weird patch?
Yeah.
Well, I didn't want to go into it because it's not that relevant for what we're saying, but I think it's the same class. Well, it's this idea that the whole dynamics of this observer in the patch should be encoded in a single time slice.
Yeah.
If you take two time slices that are very close to each other, the weird patch can overlap. And then you could insert an operator in the middle on the boundary, creating some lump of matter. And you don't know whether that observer will see or not, because depending on where you're reconstructing the experience of the observer, you will get a lot of different answers. This is something Raphael pointed out several times.
Yeah, I ask a question about the seeming paradox you pointed out about the closed universe, and because the non-perturbed universe is 1D, you can't make sense of physics. Would you say the same word for the weird patch? Same words? That, it's a big state, but of course the weird patch guy can do.
I think it has the same flavor. I think.
What is it like?
Yeah, personally, I think it has the same flavor. It's the same problem that you're trying to ask on trying to ask a local question in the bulk, but you're trying to answer using some information that only knows about the global state of the analysis.
Okay.
maybe I would point one difference between the two situations, which is if you have a 1D Hilbert space, what that really means is that there's no non-trivial commutators in that Hilbert space. So that doesn't have to do with the fact that there's only one state within the entire evolution, right? That's a stronger statement. While in the Willard-DeWitt hash, the only thing is that I think Stefano was saying is that the physics in the Willard-DeWitt hash should in principle be specified by the boundary state on that, by a single boundary state on that time slice. But for instance, if you act on that state with a commutator, you could get a non-trivial answer.
Yeah, but suppose you don't. Suppose you don't.
Yeah.
I mean,
Let's just restrict to one state of the boundary of AES. And not ever do anything to it. Wouldn't you still want to assert just like you would in the left diagram that it makes sense to talk about?
Yes, I'm just pointing out that the left diagram has an additional problem, because if we really believe that the Hilbert space is one-dimensional, then there's no commutators that we can talk about.
Yeah, I mean, there is not even, the point is that I think the commutators you're referring to are defined on the boundary theory, it is not even there in the closed universe case. So I think it's more extreme in the sense that you don't even have a system to which you can ask questions. In this case, if you're taking this global perspective.
The argument is, I think, that at some level a local observation should commute with the projection of the boundary state. And then you basically in the same problem in application. That's I think Raphael's argument, or the same equivalent to Raphael's argument.
Maybe we can talk about that.
Yeah. Anyway, this was a side point. What we will be focusing on in this talk is the first two pictures, I would say. So, one fact is that so one fact is that in this talk I will be talking mostly about the gravitational path integral rather than holography. I'll comment about holography at the end. But the gravitational path integral tells you that at least some of these issues arise from perturbatory corrections coming from wormholes. And these kind of perturbatory corrections are those where you allow the observer to, in some sense, be swapped between different copies of your system. And I will explain in a second exactly what I mean by that. Before that, let me just give another fact about the gravitational path integral, which is we know that what it computes is an average of whatever observable you're computing over an ensemble of dual theories. Now, what this ensemble is depends on the theory you're looking for. You're looking at. For example, in JT gravity would be an ensemble of random matrices. But if you consider, for example, a higher dimensional theory of gravity, maybe you can interpret that ensemble as an ensemble arising from coarse graining over microscopic data of your theory. Regardless of what's the picture, the path integral computes this average over the ensemble and therefore knows about the statistics, for example, of overlaps. Doesn't know about the specific microscopic overlaps, at least in the saddle point approximation that we generally use. So one interesting fact is that this means that if you, for example, compute an overlap between two states, and you get 0, and you can compute the square of an overlap, and you get something which is non-zero. This seems to be compatible in some sense with quantum mechanics, but what this is telling you is that those are the average of those quantities over the whole ensemble. And so you should interpret this average over the ensemble as giving you the typical size in a single realization of the ensemble, which is your dual theory, of that specific quantity. Let me put this in a practical example, which is this one. So consider a closed universe which has a negative cosmological constant, so it's touching. And those universes in Euclidean signature analytically continue to Euclidean wormholes in which you have some asymptotic AES boundaries. So you can specify states of a closed universe just by giving the length of this boundary the Euclidean past, and with, let's say, some given length, and then maybe you have the insertion operator that can represent your observer. Now, what you can do is compute overlaps, and for that you can use the Euclidean path integral. And then overlap between two such states is given by this Euclidean wormhole, which is essentially just a cylinder. Now, great. So if say that you have something like this, you will get some overlap for these states. When you compute the square of that overlap,
So just for orientation, just
Yeah.
So, I thought this close.
This
You're starting with some sort of Euclidean wormhole,
This is you.
and the two circles you're drawing correspond to the left and right side of the Euclidean wormhole. Where does your-
I guess in the closed universe you want to think of the bottom and the top as it's the Euclidean past and Euclidean future, I guess. Like the closed universe is obtained by slicing the wormhole in the middle.
Yeah, so I'm trying to remember how this works. So there's this wormhole, and there's this complete Euclidean, right, which slides in the middle, and then we continue then in crunches in both directions, right?
Yeah, that's right.
And so these,
So this is just an overlap computed by the Euclidean gravitational path integral. So a given state is specified by boundary condition in the past for this wormhole. And you compute an overlap between two such states just by filling in the gravitational path integral.
there's different analogy continuations I could consider, right, which might not lead to closed universe. But
Well, yeah, of course. You could either continue it like this, and that would be something completely different.
And then the state interpretation is different.
Yes, in that case, it's also quite troubling, the state interpretation, because I guess if you start totally continue this way, this wormhole, I guess you'll get a traversable wormhole. But the two boundaries seem to not be connected, so I think.
Right, so that's just the usual story with the ensemble interpretation of this non-factorization.
Well, at the Euclidean wormhole level, yes. The Lorentzian wormhole level, I think it's even worse than that. Because if you don't have a coupling, you got a traversable wormhole, and you really justify what's going on. But yeah, I agree that it's a push on that. Okay, so this computes just an overlap between two states of a closed universe, and then you can compute the square of this overlap. And the square of this overlap gives you just, the first term will just be a product of two of these. But then you can, at least with the rules that we usually use for the gravitational path integral, you can consider all other possible connections. And the two leading corrections would be two corrections at the left. So you connect basically a cat to a different cat and a brat to a different bra, or a bra to a different cat, and the second cat to the first bra. So these are all configurations that with the usual rules that we use for the gravitational path integral are allowed. And what this is telling you is that the variance of this overlap over the ensemble is given by these two second bras.
Before we get to the higher moments,
Yeah.
like what this will be, this inner product that you're computing here is what? It's just a Kronecker delta, right? No matter how many different.
At the perturbative level, yes. Well, it depends on what's your state. If you're defining the state, I will go into that a little bit later.
I'm trying to understand where you see in this picture that there's only one state, given that it seems like I can choose any state.
Well, here I'm just giving you one state, specified in terms of a boundary condition. This is some given cat psi j, some given bra psi I, and I want to compute the overlap between the two.
It's two states, right?
Yeah, so
And
bra
really,
and cat.
I thought the I and the J can run over many things. So.
Yeah. I'm just saying take one of these.
No, but I think the question is why is there a one dimension in this space? Like how do you see that?
No, we'll get there. At the perturbative level, it's not a one-dimensional paper.
Yeah.
That's the point. Yeah. It's give me those slides and this will become clear. Actually, the first thing is actually coming from this, because what this is telling you is that the variance of the overlap is over the one. So if you take an overlap at the perturbative level, will just be given by this. But then when you consider non-perturbative corrections to the path integral, that tells you that these two, this variance of the overlap is order 1. In other words, the typical size of an overlap in the non-perturbative hyperspace is of order 1. Now this is not immediately telling you that it's a one-dimensional hyperspace, but it tells you that it's pretty likely that if you pick two random states, their overlap is 1. So this is the first hint to the fact that that one hyperspace of a closed universe is one-dimensional. And this can be made much more precise, and I will.
This is a little bit like PSSY, but the area of the black hole at the page transition is just one. I mean, it's sort of like that. There's no suppression. And,
it's similar, yeah. So this is clear that these kind of contributions in which an observer is switched between different copies is what causes this kind of effect. So with this rule, Also with these rules, notice that there is some ambiguity of what an observer even is, in the sense that you can have a very large overlap between a state in which you have an observer and a state in which you don't have an
Sorry to
observer.
read this up to you, but where was the observer on the previous slide? I mean, in the PSSY calculating, there's no observer.
Yeah. I'm saying, suppose that you insert this mother, and you treat that as you consider that to be a model for your observer. You can have a large overlap between a state in which there is an observer and which there is not an observer.
I'm not understanding why we're using the word observer here. It seems like you could get all you want without ever mentioning the observer.
Yeah. At this level, I agree. All I'm saying is that any state and any other, okay, let me reformulate. Any state and any other state in a closed universe with these rules of the path integral have a very large overlap. I think we can agree on this.
Yeah.
So if you have a state in which there is an observer and a state in which there is no observer, those also have very large overlaps. I think this is a direct consequence of the first statement. So what I'm saying is exactly what I think you were hinting at, which is an observer in this context is not even well defined. Like, I don't even know that an observer exists, in the sense that states in which there is and states in which there is not are essentially the same state. So this doesn't give you a way to well-define an observer with respect to which you can ask questions.
So by a state without an observer, do you mean like a state without an observer but still with some matter?
For example, yes, in this case would be that.
Or even a state without
Or
any.
even without anything.
So
Zero.
you don't have to connect in this case?
At the perturbatory level, yes, but at the non-perturbatory level, you will get one even if you don't have. Because if you consider, for example, the square and overlap, you would connect the brass in a different head, and then, yeah, that's right. And this second point, I will explain in much more detail later. So let me postpone that to later, but the idea is that with these kind of rules, it's not even clear that whenever you ask questions about an observer, an observable with respect to an observer, for example, I want to ask what is the most likely eigenvalue of a given observable when my clock reads time t. This kind of question is not well answered by these generic global rules of the gravitational path integral. And I'll go back to that later in the talk, so please hold on for a second on that. But overall, our goal is to characterize some Hilbert space at the non-perturbatory level using the gravitational path integral, and a Hilbert space that is relevant for describing the observer's experience. In these kind of models that we just saw, there is not really a way to do that. And what we want to do is to try to understand what are the rules that allow you to have a well-defined notion of observer, study the Hilbert space that is relevant to describe the experience of this observer, and then study some observables on it. And we'll just label this space, this Hilbert space, by this H relational in general. Now, to do this, we need to modify somehow these rules of the gravitational path integral, because as we saw, allowing this swapping of particles and so on doesn't allow you to even define what an observer. And what we propose to do is to impose, essentially as an additional boundary condition in the path integral, that the whole line of the observer, whatever your observer is, must connect a bra to the corresponding ket when you compute moments of an overlap, for example. Or in general, whenever you compute an inner product, the whole line of the observer must connect a bra to the corresponding ket. It cannot be swapped between different copies of the system.
Can you state more precisely what that means, let's say, just in quantum field theory? I mean, are you modeling the observer, like let's say in free quantum field theory, as some wave packet gets created and then later annihilated?
Well, I wouldn't know how to even create a problem in quantum field theory, in the sense that...
No, I'm not asking you to model the whole problem. I'm just confused by this definition, even in a much simpler setting than the one in which the problem arises. I don't understand what these words mean.
I think this is automatically true in quantum field theory, because the problem here is that in gravity you can have all this swapping of operators due to the change of topology of the geometry. I don't think you can do that in quantum field theory. So I wouldn't know how to even formulate the problem in quantum field theory.
You say that we propose an observer created in a given cat must always be annihilated in the corresponding graph. I think you owe us an explanation of a mathematical definition of those words.
Yeah.
What is an observer created? What does it mean to be
Yeah. I was about
in
to.
a cat, and what does it make? What makes it an observer?
Perfect. That's what I was about to do. I just wanted to put a figure here to maybe clarify it a little bit. So the idea is that whenever you create a state, whenever you have a given state, you can specify the state in terms of the boundary conditions to the gravitational path integral, right? The gravitational path integral will prepare your state for you. And if you have a given observer, which in this talk we will model by an insertion of a matter particle essentially, but in general if you have an observer, the state of that observer will also be specified by the boundary conditions that you give in a given state, in the preparation of a given state. So what you want to impose is that if you take two such states and want to compute an overlap between the two of them, then you must impose that the word line that the observer is created in this state and indicated in the corresponding cap when you compute an overlap. In particular, if you compute, for example, a square of an overlap, you don't allow the observer to be swapped between the two copies of the system. Does that answer your question?
Maybe. So you're talking about creating and annihilating the observers on the
In the preparation of
on the asymptotic boundary of the Euclidean continuation of your closed universe.
Yeah.
And
But the point is that that's how we compute overlaps in quantum
the
mechanics.
observer, so there's a preferred state which is like a vacuum or something on those boundaries, and the observer is an excitation about that.
Yeah. For example, you can think of it that way. So you have, say, an insertion of a particle, other particle, that models your observer, and you don't want to allow configurations in the gravitational path integral in which this particle is created, is like part of a given graph, but annihilated in a different cat when you compute, for example, the square of an overlap. Or the expectation value of a projector, same story.
Sorry.
Yeah.
That's a question.
Yeah.
So, I just got, just now, I'm confused by something. Is this the definition that only makes sense if there is like a geodesic or a saddle point associated with the observer?
No, in geometric gravity, for example, you can sum over, you impose this as a boundary condition, then you sum over all possible geometry that allow you, that
No, this
are compatible with
this criterion of forcing this thing to go here.
yeah.
Only.
No,
Does that make sense?
It doesn't
Beyond
need to
saddle
be.
point for the line?
Yeah, like if you had some many connected geometries, like there could be some amplitude for it to go in one place and some like it was really quantum, it could go in many
Right.
It's maybe not well defined where it went, if it's not a heavy object.
Well,
Right,
it
so
is well defined as asymptotic, that a specific
If it's something that follows
word
a
line
really
connects
safe.
the parameter corresponding.
Yeah, if it's a word line, right? Like I think he's
That's
saying
what
like
I'm
if it was a
saying.
light, like
Suppose it
1
was
or
like
something.
something that delocalized or something.
Yeah.
But I think in geometric gravity you can always express it in terms of a word line.
It's a massive particle without mass or something, or
I think in geometric gravity this is more generic than that, but in you're asking, I guess, in a higher dimensional setup.
yeah, just some
Yeah.
something,
In some setup in which you cannot just treat it in the saddle point approximation, I guess you should think of it as having some given, basically the same insertions in the prime and the corresponding cat that allow you to create this observer.
Yeah, you can create them, but it's in everything. But you're throwing away some geometries there, right? Is it clear the rule for throwing away geometries if the thing that's propagating between the boundary is not following in geodesic, or like it's not in some sense a saddle? Not the geometry being a saddle. I mean
So you're asking if you don't even have a word line. That's it.
right. Yeah. I mean, maybe observers are always word lines. I don't know, but.
I mean, to some approximation, if it's heavy and
I've turned to decide if it's a limitation or it's like a fundamental. Like,
Yeah,
it's
I
not
didn't
necessarily a limitation because fundamentally observers are word lines. I don't know.
Yeah, I didn't think about this specific configuration, but the idea is that I would say, okay, at a high level, I can say that for an observer, you should think of it as something which is localized on the state that you're preparing. Otherwise, I don't know what you're talking about, an observer. So maybe if you have, say, a distribution of particles inserted here that then focus on a given slice where you define your state, then that is your observer, and that's what should connect to the corresponding cat in the gravitational.
I think it would be like, could you discuss this entire program without saying observer? Because you have the second line here, which says that this is equivalent to introducing an additional boundary.
Yeah.
And so I think from a mathematical point of view and writing down some well-defined proposals, it sounds much more promising to me that you might have the chance of maybe defining exactly what this boundary is supposed to do, what its shape, what specifies this boundary, and how does it constrain the gravitational path. I mean, I don't live in Euclidean time. I wasn't present at the beginning.
Well,
of the
but this
universe.
is
I'm
not.
not at asymptotic infinity. So these observers are not like me at all.
Wait, I don't think I agree with that last statement in the sense that this is just a way to define it between states that can have a good interpretation of rest and signature. So these observers well, okay, this is JT gravity, so no, might as well be you.
You haven't defined what an observer is, other than indirectly to say it's a world line that actually is a new boundary.
This is just a way to define
anything else, right?
This is just a way to define the inner product, which is relevant in order to describe the experience of whatever is along this boundary. The specific model, I will go into some more detail of what we mean by an observer, but at this level, this is just saying what is, if I live along a world line, and I think that is true for us, and you can do this in parentheses, just a way to specify the inner product with the states.
But I don't live for very long, and it doesn't seem to matter. Like the universe is 30 billion years
Yeah,
old.
but sure, but this is the way to prepare a given state, right? Then I can
But I
evaporate.
wasn't prepared this way. I'm not some single solid object.
You can always
Without going into details. I don't think you can trace me back to the Big Bang or along a red line, let's put it that way.
But it's not tracing you to the Big Bang.
Or to an asymptotic boundary for that matter.
Well, it's an analytic continuation to Euclidean signature, but here the point is not the asymptotic boundary. You could prepare the state on any time slice you
Yeah.
like. The point is just to compute inner products between states where the observer is well defined on any time slice.
You could just as easily think of these guys as preparing a state that then lives with a time signature slice. So
Yeah.
yes, it equals 0.
So you can think of just a state living here and computing overlap between two states. Just define on this time slice. It's just a useful trick to defining asymptotically. But
I don't think I arose from analytic continuation either. I just don't think that that's the way out. It's not.
But
But
the thing that Ahmed said is a state directly in Lorenz's signature.
yeah.
It's the time symmetric slice is a state of the closed universe in Lorenz's signature, and you could also define other states in Lorenz's signature.
Yeah.
This is just one
One way
class
to
of states that
compute
you
it.
can construct.
Well, this is a state more generally where I've inserted an operator at the asymptotic Euclidean boundary. I've done.
No, like, but it's a state where you insert matter on some time slice.
Yeah.
The asymptotic boundary, I think, is an example.
Just a way
for
to label
inserting-
states. It's a basis.
In gravity, I don't know how you insert. What do you mean by inserting an operator on time slice?
Well, we have, let's say I want to analyze the state of the closed universe that has some size
Yeah.
and some, matter excitation at some location in the closed universe.
Yeah, but I don't. You know that I don't get to do that, but I don't get. I mean, I'd have to do all of that reaction, and there's also people worry about all the variance of this thing.
Yeah, the gravitational path integral automatically, when you compute the inner product, it automatically implements both gauge invariants, and it automatically tells you whether how the geometry has to be modified because of the back reaction of the particle that you inserted.
Yeah.
Wait, so what does this constraint on the world line mean from this perspective? You constrain some fields of the world line.
It just answers that if you're trying to compute some quantity, which is not simply an overlap between two states, but for example is an expectation value of project or something like that, you must connect, that observer must be well defined at the state where you are trying to compute this.
So you think you're just preparing the observer state?
Yeah, it's preparing the observers and the system state.
Are you constraining the gravitational path integral, or are you constraining the states?
So I think the problems that the problem that you're bringing up appear even at the perturbative level, forgetting about these fancy moments, right? It's how to define the observer at the perturbative level, right? And we're just saying that in the closed universe, you just take a time slice of your closed universe. It could be in the analytic continuation, this has a non-infinity boundary, or it could be another time slice that's specified in terms of, I don't know, let's say the extrinsic curvature and the size of the time slice. And you specify the, gravitational state on that slice, and you also specify the matter wave function on that slice. That defines a state, right? And an observer is just some sufficiently, some excitation of the matter fields.
And that formalism, I know I don't have this problem of dealing with only one state. I'm getting lost now because this is not the setting in which we were trying to resolve any issues about.
No, I was just explaining the perturbative setting, because the problems that you brought up appear at the perturbative level. You're saying that at the perturbative level, we're not an observer that was
a
created.
field theory state on a fixed background. Is that what you're saying?
And you could also consider the back reaction of the matter fields on the gravitational theory, right?
Right.
And the state can be prepared using the gravitational path integral, or something like that, right?
But what does that have to do with gravitational path integral? So I'm not understanding this language. This seems like semi-classical gravity or something boring,
Yeah.
so we're not doing anything
Yeah.
interesting at all.
Right, that state can be prepared using the gravitational path integral. Would you agree with that?
I think we've lost track a little bit. You're trying to introduce something very fundamental called an observer, and I'm trying to understand what it is.
What I'm saying is that these states can be defined at the perturbative level, say at a time slice, for example. And then you can use the gravitational path integral in order to compute overlap between these states, right? And the transition amplitude between different states, or the expectation value of some operator. And
But I'm trying to understand if
that's where
we don't say the word observer, but just stay within the formalism that I think you're using, which doesn't invoke any kind of novel concept so far, right? Then in the language of that, are you defining a new gravitational path integral that is subject to new constraints? I was hoping you would tell me that, yes, I am, because I'm effectively just introducing another boundary, and here are the rules associated with it.
yeah, so if you want to frame it in the terms of states on a slice, what I'm defining is a new inner product at the perturbative level.
And is there some way of just stating that mathematically in terms of taking the boundary and the rules surrounding that, or something like that? Like, is there some statement like that?
Yeah,
Doesn't
what I'm
invoke the
doing
word
is-
observer.
Give me a state of quantum gravity on a given slice. What I'm defining is a new way, a different inner product from, at the non-perturbative level, a different inner product from the one that we were defining before.
And you're gonna tell us how to define that in terms of the language?
On the gravitational path.
Yeah, just geometric or some language that's mathematical.
That's right. Good. So at the perturbative level, the inner product is the same. At the non-perturbative level is where the inner product is different.
Sorry, at the non-perturbative level, it's gonna be different from the inner product that you discussed earlier.
From the non-perturbative inner product that we usually define with the
The only
gravitational
thing
path.
here is at the non-perturbative level anyway, right?
Yeah. So at the perturbative level, the inner product is the one you would expect. At the non-perturbative level, there are two inner products. One is the one that is defined with the usual rules of the gradation path integral, and one is this one.
Okay.
And those are not equivalent to each other, which means that the non-perturbative Hilbert spaces are not the same.
And the key thing is that you're requiring every state to contain somehow a particular excitation or something like that.
Yeah, because the question that you're asking is that a question related to the experience of the observer. For example, you want to say that you want to compute some observable dress to a given observer. It wouldn't make even sense to ask the question.
I think these words a lot. What does it mean to dress an observable to an observer?
For example, if I have a word, this is goes back if you want to that sort of CLPW.
Yeah, I didn't understand what it means.
Well, if I want to compute an observable and if I live on a given word line, I can, for example, specify the location where I insert an operator in terms of what time my clock rings, right? This is one way to, maybe the basic or the zero way to think about it.
Normally when we say dress, it means like where the field lines go, which doesn't seem to be related to what you're saying.
Well, if you want, you can consider a Wilson line that is addressed to the word line of the observer, which creates it. For example, the secret.
You have an observer with some continuous spectrum and they can absorb any energy required to
But that's,
do some local
if
dressing.
that observer still lives in a gravitating space-time, then that's not consistent. I mean, here everything's a closed universe, we don't get
We
to
do a measurement, right? How do we not, the measurement doesn't conserve energy, or we can the reason it doesn't need to is because we use energy during the measurement.
I mean, just at this non-perturbative treatment, this is a very ambitious sort of level of treatment, right?
Sure.
So we can't discuss like having an infinite energy spectrum, let alone continuous, like it's just not completely consistent with log.
That doesn't assume that.
Yeah.
We're not assuming that. You could ask an observable, I don't know, the stress tensor measured along the world line of the observer.
Yeah.
The maximum value of the stress tensor that the observer sees. What's the probability distribution for that? That the observer sees a certain value of the stress tensor. As an example of an observable. That's dependent, that's dressed to the world line of the observer because it's evaluated on the world line of the observer. Just as an example. Or correlation functions measured along the world line of the observer. That's another observable that's stressed.
I think by doing that, you're giving the observer a continuous spectrum.
I think if you want to localize it exactly,
Putting operators along the world line.
Yeah, if you want to localize
Yeah,
the
that's
operators
exactly.
exactly, yes.
And if you smear them out around it and you define them relative to it, then you're going to end up like breaking Einstein's equations at the location of the observer in a way that is not conserving energy.
I actually totally don't understand this. Like, if I do an experiment here, and the reason that I get an answer for the expectation value of the stress tensor is decoherence, right? From this global perspective.
No, I said the
nothing is-
probability that you see the certain value of the stress tensor. Yeah. But yes, sorry, go
But
ahead.
even so, like any outcome, I mean, none of this really happens, right, in this global description. It's just some, I mean, this is just some state, it'll be a little bit patched, you know, I can look at it, it's completely entirely equivalent and all different slices of the little bit patch. I don't think it actually matters if you were just close or we consider it a little bit patched, maybe, yeah, it makes sense to discuss my observations.
I think that's kind of the problem, right? Like, it doesn't make sense to discuss that, but clearly these are like all things that are useful to be able to calculate. Like, it would be nice to be able to calculate 2-point correlation functions around my road line, but I don't have the tools to do that, and this is one way to put this tool.
this is a proposal for how to look at what non-perturbative quantum gravity effects an observer could see within a framework in which globally nothing is happening. This is the way to think about it.
I think in your example with decoherence is great, and assumes that the observer is a more complicated system that interacts with the other fields in the theory, right? And that's why you give the observer a measurement apparatus, and you interact with the environment in such a way that the state of the measurement apparatus is correlated with the actual stress tensor that you see, right? But that doesn't mean that you cannot make predictions of what the stress tensor should be that you see before you model the observer as this more complicated apparatus that decoheres with the environment.
I just feel like there's a resolution of these issues in the context of like a single state setup that doesn't require gravity. And that's if we just treat, for example, the galaxy as an isolated system in a single quantum state, and we want to understand why we see outcomes of observations. And it's absolutely critical to trace over an environment that we have, right? So we already get that.
No, but I think the problem with this one-dimensional universe is more severe than just saying that that the universe space is one-dimensional. Is more severe than saying that you specify some unique state for the galaxy, and then you evolve, you perform time evolution through the Wheeler-Lewis test, right? And the state essentially remains the same. For instance, one issue if you really have a one-dimensional Hilbert space is if you were to measure a commutator in a one-dimensional Hilbert space, the commutator of two operators, right? You would find that the commutator always vanishes for any two operators in a one-dimensional Hilbert space. While in your example, if I just talk about quantum field theory, a state of quantum field theory of the galaxy and evolve that with time, I could measure a commutator of two operators and see that it doesn't vanish. See that it has non-trivial eigenvalues, so on and so forth. So I can talk about the probability of being in a certain negative state of the commutator. I cannot do that in a one-dimensional universe. I need two operators to meet. So
Well, I don't understand why that universe couldn't be one-dimensional in exactly the same sense that if I fix the state of the galaxy once and for all, we could still have experiences. The reason I'm bringing this up is that, the decoherence and tracing over a large part of the system is so vital for our experience. Like when we discuss an observer, I feel like that should be the first thing we talk about. Like any model that doesn't build that in already has no chance of describing an observer. Like this seems like such an esoteric problem to solve. If you're ignoring this in a very pedestrian way.
I don't think so, but maybe we can discuss it.
Yeah,
And I can explain why I don't think so.
Yeah.
So what's the model for the observer? Is just a particular index J, or is it like all indices?
I'm going to it in a couple slides if you. 45 minutes and 4 slides. Hope you're not transport tonight, guys. Okay, so I think one thing we can agree on is that these kind of rules prevent those corrections that we saw in the 2 slides ago, half an hour ago, where these kind of contributions cannot contribute, and so clearly this tells you that, for example, the dimension of the Hilbert space that you can compute using the gravitational path integral will not be one-dimensional in this. Will not be one-dimensional. So this is just because with these new rules, you will have, you will force this observer to connect the parameter corresponding to cap, and so the first correction to the square of an overlap will not be a factorized contribution, but will be something like this for boundary geometry, which is number to Berkeley Center. So let me give you a summary of our results, and then we can go into some more detail and see how far we get. But the idea is that our proposal, as I said before, just defines a new inner product and the non-perturbative method for these quantum gravity states. And we studied it in JT gravity, but it should be pretty simple to generalize at least in some setups to higher dimensions. And the idea is that for a closed universe, you will find that this Hilbert space is not one-dimensional, but rather it's actually quite large. It scales with e to the 2 and not to JT gravity will matter, which means essentially to the 1 over G Newton. And we did the same calculation in the double-sided black hole case, and you see that also that Hilbert space is actually quite larger with respect to the usual Hilbert space. Then one can study observables along the observer's world line, so this kind of dress observable that we've been talking about. For example, you can take a closed universe with a world line and an observer and insert 2 operators along the world line and study this correlation function between these 2 points. And you will find that unlike what happens in the previous, with the, let's say, old rules from the gravitational path integral, in which this observable is trivial, it's just a multiple of the identity, because the Hilbert space is one-dimensional. In this case, the perturbative answer to this question will be the dominant one, and you will get a non-trivial answer. And finally, we also looked into the 2-sided black hole case, where you consider an observer jumping into the black hole and compute the center of mass collision energy with a shock wave coming in from the left side. And in that case, we find that effective field theory, let's say the perturbative answer is the relevant one until exponential times, in the exponential time for when the observer jumps in. And this is in contrast with some results from last year that suggested that this breakdown actually of this perturbative answer due to non-perturbative effects arises at times over the phase time, so linear time. And one thing I want to say is that our proposal is that this kind of, these different rules for the path integral should be used when you're asking questions about some given observable in the presence of a given observer. If you're trying to ask some global question, for example, a boundary question in the CFT, then you should not treat this observer's world line in any different way as the rest of the matter. Okay, so let me give a quick review of genetic gravity. So genetic gravity is a Pinadon gravity theory in two dimensions. It has a topological term in its action. It has a term that imposes essentially the phase curvature for the space-time, and we will take it to be negative, so a hyperbolic space-time. And then we will take, there is a boundary term in the action that encodes all the dynamics of the theory, and that's a matter action whose specific form one vector. This theory at the perturbative level is just the quantum mechanics of a single degrees of freedom, this length. You can think of it, for example, in the two-sided black hole case, as the length between two asymptotic boundaries on the right and left of the black hole. And you can just define a Hilbert space at the perturbative level in terms of this length, where you have a basic states which are delta function normalized. If you have matter, and it doesn't really matter what's the form of the matter action, but if you have matter, what you obtain is that this matter must transform under some given representation of the SL12 group of ADS2. And what you get is that states can be labeled by the same length as before by Casimir of this representation and by one quantum number labeling states in the representation. So these delta M states, which are also delta function normalized. Once you have those, you can make a change of basis, and this is, for example, for the two-sided black hole with matter. You can just label states by this delta, this Casimir representation of matter, and then the energies on the left and right side of the black hole, and that fully specifies your state. And you can also transform that and define states in terms of delta and the length of the asymptotic boundary on the left and right of the matter insertions. In terms of the length of the asymptotic boundary, preparing the state of the two-sided black hole on the left and right of delta. Let me specify what I mean by that. You have an insertion delta in the Euclidean path, preparing this two-sided black hole state, which is sort of a thermophile double with matter inserted. And you will have a beta left, which goes from this green point to the symmetric point here, and the same on the right side. And those will be your beta left and beta right that specify the given state. Then you can compute, for example, overlap between two such states, and what that gives you just a dispartition function of genetic gravity in the presence of matter, which can be computed explicitly, and in particular we scale with e to the s naught, which is the scaling, a Euler characteristic of the disk. And then you will have two integrals over energy. These s are just the energy, square root of energy, weighted by the Santanzica states and the Boltzmann factors. Gamma delta is just a normalization factor that I will not go into any details on. So this is the more familiar case of the two-sided black hole. If you think of this as essentially overlaps between two thermophile double states. For a closed universe, you can do something very similar. So to define a state of the closed universe, you can express that in terms of some boundary condition in the path integral. And this boundary condition is just labeled by the length of the boundary of the Euclidean path and the scaling dimension of an operator that you're inserting.
So this is the closed universe that we were getting as an analogy continuation from the Euclidean wormhole in this very same theory, right?
Yeah. This is like just the way, at this level it's so perturbative genetic gravity. You can just define a state by specifying the length of the asymptotic boundary in the Euclidean path. and a given operator insertion. That uniquely determines, for example, the length of the reflection symmetric slice at the perturbative level of this cylinder. And the state of the closed universe, if you want, you can just define it directly there as the length of this reflection symmetric slice and the scaling dimension of that.
We imagine that this is somehow an infinitely heavy particle or something, so that we can see the right line.
Sorry, if you have particles to that?
I'm still really struggling with this idea of a world line, and the fact that we're treating this so classically. This is infinitely massive.
Well, in the case of GT gravity, you always have a word line. I think if you want to do this specifically with a word line localized in higher dimensions, then you need to put the geodesic approximation.
But even in JT, if you want to stabilize this as a saddle, don't you need it to be heavy enough?
I think you need just to have a matter particle.
Just any matter?
If you have just an empty universe,
Yeah.
then the wave function of the closed universe will be peaked at a length of the circle of the minimal geodesic, which is 0.
Yeah.
But if you insert the matter particle, it will be 0.
I'm pretty sure you want this observer to be something that's much more absolute than that. In the real world, massive particles can be liberated, they can be annihilated. There's no essentially identity of one of these things. They're, in fact, famously non-distinguishable. So, how do you reconcile that here? I mean, don't you want to be taking
I still don't understand this connection between a matter particle being created and annihilated in Lorentzian time with the idea of preparing the state of a particle in a given state using the Euclidean method. I think that's two different things. Like if I want to just, when you say a matter can be created, yeah, but I can give you a one particle state. This is just a way to prepare a one particle
state.
state.
Last across the entire, I mean, for an infinite Euclidean time.
Yeah, but this is
Not
just
that
a way.
difficult.
This is just a way to essentially, you want a one particle state, then you can do whatever you want with it. You can manipulate the particle. This is a way to just define the one particle state using the Euclidean method.
What if there are more particles like this in the universe? Which ones gives a...
Say, you can define multiple particle states.
No, but you can want a single one of them out.
Not at this level.
Not at this level. This is
This
perturbable.
is the definition of the inverse spread.
Yeah. This is just a definition of the state.
Yeah, so I don't think you need to even draw that word line, really, right? Like, I mean, if you,
I mean, you do
I don't
because
understand what you mean that in JT you always have a word line. I don't understand that.
But, well, if you don't even draw the word line, if you don't have matter, you
Well, you just can draw the
insertion of an operator.
points on the lower.
Yeah, I think the more precise statement is that the world line, the sum over world lines in between the 2 points, the geodesic approximation is one big fact, which means that the sum over all possible world lines that don't necessarily even travel along geodesics are well approximated just by the geodesic approximation. Even if the mass is not very heavy. But that's still true, it's still e to the minus delta L with delta equal 1.
Okay, so you can like take some meters out of we want to present and then set it to 0, and you make it like so.
Yeah, the
Yes, it was the same as if you did the geodesic approximation.
Yeah, the world line approximation gives e to the minus ml, and the one loop determinant corrects that from e to the minus ml to e to the minus delta L, where delta is the scaling dimension.
So
of
it's
the
very
field.
special. It's like,
Yeah, but that's not really important.
it's not.
Yeah, it's very important for this.
Well, so this is a completely different way of defining the Hilbert space than the talk in a way, right?
Yeah, I mean, it is a different Hilbert
Yeah,
space. And that's the Hilbert space
Yeah.
of a black hole, this is the Hilbert space of a black hole. Yeah. But it is the same sort of construction to prepare it, but of course they define different Hilbert spaces. If you slice path integral in different ways, you get different Hilbert spaces. So, both of these Hilbert spaces are actually infinite dimensional, and the simplest way to see that is that these delta function normalized states specified by the length, for example, are a delta function normalized, and the length is a continuum operator. So really you have an infinite amount of states that are over top of each other. So what happens when you include non-perturbative effects? And this is still before all our construction, this is just what happens in general. It happens that these perturbatively orthogonal states can be non-perturbatively non-orthogonal. And this is due to these wormhole corrections that we saw before. And I already said that this gravitational path integral compute the statistics of, for example, these overlaps, and by averaging over the dual sample of theories. And the fact that you can have two states that are orthogonal at the perturbatory level, but non-orthogonal at the non-perturbatory level due to these corrections, means that the non-perturbatory Hilbert space can be much smaller than the perturbatory one. Turns out that the path integral is actually very powerful in computing how much smaller, so into computing what is the exact dimension of the non-perturbatory Hilbert space. And generally you can do that using this resolvent calculation that maybe for the sake of time are now not going to a review of, but the idea is that you can take k states, which are orthogonal at the perturbatory level. Then you can compute the resolvent of the grammatics of overlap using the non-perturbative inner product. And then you can compute the dimension of the span under the non-perturbative inner product of these k states by integrating the trace of the resolvent over some given context. So this is just the fact that the gravitational path integral is actually quite powerful in computing the dimension of a Hilbert space. So this is a calculation that Ahmed did, which I think was very, very interesting, which is just use this resolvent calculation that was, I think, pioneered by Jeff and friends in the BSSY paper to compute the dimension of a closed universe Hilbert space in JT gravity using the rules of the path integral. You can expand this resolvent in a series and then compute it using the gravitational path integral and resum this to obtain an expression for the resolvent. Once you have this expression for the resolvent, you can integrate it over the contour, and it turns out that whatever number of states equal by k you get, you always get 1 from this integral. So this means that if you take k states, which are perturbatively orthogonal, so you would expect at the perturbative level a Hilbert space which is k-dimensional. It turns out that non-perturbatively they're all linearly dependent from each other. So they're essentially all the same state. And the Hilbert space that you get is just a one-dimensional Hilbert space.
So here you haven't used the rules you specified before, right?
No, this is with the old rules. So this is just a proof of the one-dimensional Hilbert space for a closed universe. Okay, some more details about the model of the observer. So now that we have these, let's say, previous results in hand, we can see how they're modified by the rules. And this is a little bit of more detail of why an observer, what an observer is in this kind of model. So in our model, we will have an action for an observer, which can be, for example, a very minimal action, similar to the one that is used, for example, in the CLPW paper, where you just have a simple model for the observer with an Hamiltonian Q, and the observer has a bunch of energy levels. Now,
is this part of the? Is this an external system for mathematical purposes? I know you want me to think of the observers being inside this universe, but this action seems completely unrelated to the JP action we wrote down earlier.
Yeah, you have the JP action plus the action of the observer. This is the idea.
It's an I sub m G5.
You have the same action we had before, plus the action of the observer. Yeah. So, given that, the kind of state that you would generically prepare is in the path integral, some state, let's talk at the perturbative level for now, is a state which is, say that I want to have this observer in the closed universe, and I want to have some other particle. So I do a one particle state essentially.
Does this observer gravitate in that closed universe?
This observer gravitates in the closed universe.
Then why isn't it already part of the action that you had before?
Well, just like you need some action for matter.
Yeah,
yes,
it has some action for matter. So I thought it was important that everything is coupled consistently to gravity. Is that just another term of the action for matter?
That is, I mean, that observer is coupled to gravity. You have just an integral over the word line of the observer, which is fluctuating in the space-time.
But the observer is almost quantum mechanical, right?
Yeah, everything is one.
So it's like infinitely localized. I don't understand how one could couple that consistently.
Can you clarify what you mean by that?
Like if you imagine adding like
Maybe
a
there's
point
a-
master vacuum, if you imagine adding like a point master vacuum, like just an M apple.
Yeah, well, certainly 3 dimensions I can't do that. This is something that's specific to the 1 plus 1 dimensional model. In 3 dimensions is inconsistent, right? Because it's to relate the inside black hole that it made. Is this battery consistent?
No, I think in 3 dimensions it will create a conical singularity.
Yeah.
Just like a Monte Carlo.
One part?
Yeah.
In 3 plus 1 is what I meant, sorry.
Oh.
Yeah, in 2 plus 1 it was create a conical singularity, that's right.
3 plus 1, you could specify the action on some like world volume. If you want, you could smear this observer a little bit.
I think this is sort of related to some of these first versus second quantized questions we were asking before. I think you have to worry, like in the real world, that excitations spread out. They're not somehow, they don't carry a label on them. Here I am, I'm the special one. This seems like you carry a label on it. This is the observer. It's a very special excitation that's like specially labeled, specially added to the theory.
Well,
That's
you,
true, right?
you do carry a label in the sense that if you're making experiments, right, whatever experiment you're making is made along your own work line. That's what we're trying to, this is
When I
cool.
make experiments, I'm a totally emergent approximate concept. If a meteorite crashes into Earth right now, right here, like what am I the next day, right? This guy is still there.
That's the part that they don't
Like this guy
really-
cannot be destroyed by a meteor.
Yeah, but that's just because you didn't couple this world line to the rest of the matter.
Exactly.
But that's a simplification.
No, once you do, then it's no longer clear about the observer. Because it's all just one big mess.
Yeah, but the same is true when we perform experiments, right?
Exactly.
To describe what
Exactly,
we
which
see in
is why I think
experiments,
this
it's
doesn't
all one
capture
big
it.
mess.
This is
No,
not one big mess, which is why I think it doesn't capture it.
well, we can debate that afterwards, I don't want to take over the talk.
But in principle, is this supposed to emerge from the matter action? Like there's JD action plus matter action plus this, or this is secretly part of the matter action?
This is, if you want, in the previous case, you could think of 2 matter actions. One is for the rest of matter, and this is for the observer.
So this is like some special thing. It's not just coming from one of the fields.
No, it has its own interface.
But you could think about it as emerging from the
Yeah.
matter action as, you integrate out the matter,
Yeah, that
and
makes
you just insert the operator.
some heavy operator.
Yeah, but you
that I understand.
But you need to
Then
treat-
you end up with this world line action, that's
Yeah.
the idea.
Yeah, that I
But since you're treating differently than that specific matter insertion corresponding to the observer, you would have some word line action.
This is like the former Roma code, special.
Okay, what?
Sorry, I was alluding to your favorite song.
Well, please don't. It's already a tough time with all these questions. You don't need to please. Okay, so you can consider the states in which you have states at the perturbable level of the gravity labeled by the scaling dimension of the observer, the scaling dimension of the matter insertion that you have, and the length of the asymptotic boundaries on which you are defining your boundary conditions in between the observer and the matter insertion. And then you have the Hilbert space for this observer, which will be just labeled by energy of instance of the observer. Now, what we propose is that using the gravitational path integral with our rules to compute overlaps in between any of these two states and including a perturbable correction, we just define this Hilbert space, which is given by H relation of perturbable times this observer integral space. So what we'll do next is see how the calculation of the one-dimensional Hilbert space is modified with these rules, and so compute the dimension of this Hilbert space. So what we're focusing on is computing the dimension of the Hilbert space for the gravitational system with which the observer can interact. And it's important to notice that we also have the Hilbert space for the observer, and if that Hilbert space is very, very small, then the observer can only probe a part of the system. It cannot learn too much information about the system, because if I have 2 qubits, I can only learn about 4 states. So the amount of information the observer can actually learn about this Hilbert space is bounded by the dimension of its own Hilbert space. But what we'll be focusing on is the Hilbert space of the system in this context. So maybe I think this was a good point to maybe explain why these rules made sense. So maybe let me go through these and imagine that it was based on rules.
Tomorrow?
I'm not here tomorrow.
Okay, sorry.
Okay, maybe let me explain these, the calculation for the closed Hilbert space, and then we can see if we can keep going. So let me just say that the observer has a bunch of energy eigenstates. And if I want to define a clock, what is a clock? A clock is a physical system that has a bunch of energy eigenstates, and a given time for a clock is specified by a specific superposition of eigenstates for this clock. So what I can do is just define a state for the observer, which is time equals 0, by some given superposition of its own energy eigenstates. For example, I can define a state using these asymptotic boundary conditions that prepare the observer in a state where their clock reads time equals 0 and the reflection and the minimum geodesics lies in this closed universe. So that just defines a state, even in Lorentzian signature, in the closed universe in which the observer's clock reads 0 and the system is in some given state. Then I can ask a question, which is, what is, for example, the most likely eigenvalue, or what probability does an observer have to see any eigenvalue for a given observable A when their clock reads time 0? So the answer to this question is in computing the expectation value of some projector onto the eigenbasis of the operator A in a state in which that I prepared when the observer's clock reads time 0. So this is a quantity that will answer that question. And in terms of the gravitational path integral, you can formulate the question in terms of some boundary conditions to be filled in. What are these boundary conditions? Well, I will have the 2 boundary conditions that will prepare my state of the observer. And then I have the projector, which is just a sum over ket-Brown. This is, let's say, this minimum geodesic slice. These are eigenstate of the a sum of the eigenstate of the operator A, where the observer clock reaches time 0. And I can rewrite these states, as we mentioned before, in terms of asymptotic boundary conditions as well. So what I need to do now that I set up my boundary conditions is to use the gravitational path integral to just fill them in and compute this expectation value of the projector. Now what happens if I use the old rules? It happens that I can connect any boundary to any other boundary and obtain these 3 contributions, just like before. Now, this contribution really computes a transition amplitude between the state I'm interested in, with observer's clock time equals 0, and a given energy, A eigenstate, with observer time equals 0, and then square that amplitude. So this is really computing what I want to compute, which is the probability to see a given eigenstate of the operator A when the observer's clock reaches time 0. These other 2 contributions compute something quite different, because this, for example, is computing essentially the norm of this state and the norm of the projector. So it's not quite the question that I'm asking. It's not computing that transition probability between a given state and a given state in which the observer will read an eigenvalue for A. And something similar can be said for this other contribution. So this rule seems to not really answer the question that we're asking there in the box. If you use our proposed rules, what happens is that those 2 are automatically excluded, because the observer needs to connect between a bra and a given cat. So this cat could have bra in a projector, and the cat in the projector to this bra. So the only contribution that remains is its one. So this seems to suggest that these rules make sense, at least to compute some question which is relevant for the observer's experience. So essentially the question, what will likely an observer measure for this operator?
So just, I think we tried to but just make sure. So if you completely exclude them, you just make you have the uncovered background. If
Yeah.
you don't exclude them, you have a small correction, but you're not claiming that that small correction is measurable.
Well, if you don't exclude those,
So you just say they're suppressed. Oh, so you are excluding them.
I am excluding them. There are
some other
there
geometries.
is plus and for boundary.
Right. Okay.
The four boundary
So,
work will be
so what
similar.
you've drawn there is just one of the character facts.
Yeah, this is the perturbative answer, I guess, which is true and leading order. That's the difference. If you use those rules, the perturbative answer is correct in the leading order. If you use our rules, the perturbative answer is correct at sub-leading coordinate to the matrix not, which would be a four boundary form of the one I showed before. Okay, so this suggests that at least these rules make sense for this kind of question. Maybe what I can do now is give you the answer for the closed universe hyperspace in 5 minutes, then anyone who wants to leave can leave, and then we can discuss observables afterwards in another 10 minutes in future direction, which I think could be quite interesting. So what can we do is we can compute the dimension of this hyperspace for the closed universe using our new rules, again using the resultant calculation. And we can specify states by the boundary condition for the observer, and I'm going to simplify as much as possible by saying, okay, insert a matter particle with a given flavor I fix all scaling dimensions, I fix beta left and beta right to be the same. And this, of course, at the perturbative level restricts to a small subset of states, but we will see that these are enough for k sufficiently large, which is the number of flavors, to span the entire non-perturbative space. So, with our rules, the dominant contribution to an nth moment of overlap is given by a fully connected geometry. And this fully connected geometry will have, say, this is for example for the third moment of an overlap, you will have an observer connecting bra to the corresponding cat always, and then mother particles can connect different couples. This can be computed explicitly, that's the formula, and then you can compute the resolvent. So what's different is resolvent with respect to the previous one? It's just that for the first moment it's the same. For the second moment, you have this boundary condition given by the red lines up there that impose that boundaries must connect, the bra boundary must connect to the corresponding cat boundary. So the first correction to the square of the overlap will be a 4 boundary overlap. This is the same that happens in the observable that we saw before. You can reorganize this in such way as an equation, compute explicitly the resolvent, take the trace, integrate it thanks to the analytic properties of the resolvent that Quanta worked out, thank you. And what you get is that the dimension of this hyperspace spanned by k states, the non-perturbative hyperspace spanned by k states, is the minimum between k and d squared. For d squared, scales with e to the 2s naught, so it's basically e to the 1 over 2. This means that again, if you take just a few k states, then you will have a hyperspace that these are all non-perturbatively orthogonal, and at the hyperspace spanned by those k states will just be k-dimensional. But if you take many of them, then this dimension with saturates means that any additional state that you take will be linearly dependent for the previous d squared that you had. And so the full hyperspace for this system will be given by a dimension d squared, which scales with 1 e to the 1 over g. So the difference is that before we had a one-dimensional hyperspace. For the closed universe, now we have something which is exponentially larger in 1 over g. And this was done also in the two-sided black hole case, and we found that the hyperspace in this setup actually tuples in size. So now I was going
squares in size.
Sorry?
Squares.
The number that is of freedom tuples.
Yes.
Squares in size. now we're going to go talk about observables. Should I or should we stop
Maybe
here
we should
and
do
keep,
the thing you suggested, right? Like,
keep going for whoever
like
wants?
stop officially, so people can read it if they want.
That's it.
Okay, that's nice step on the questions for people who want to leave.
Sorry, I asked it that way.
Okay. Anyone who wants to stay? I guess that's the important question.
Yeah,
Okay, anyone who wants to stay? Okay.
yeah.
Let's keep going. So far we've seen these properties of the Hilbert space that we get. But we,
Like, I don't want to leave, but it can also.
Yeah.
Okay, yeah, so I mean, like, it's just a little bit, like, maybe the logic is not very clear to me, but, so you create, you use I of the, like, flavors to create, like, a complete set of states.
yeah.
Yeah, we know that the K is large enough, it's separate,
Yeah.
that's fine, but it's just like, in my previous understanding, like the separation is due to the non-perturbative correction. But now if you're in the closed universe, you just have a one-dimensional Hilbert space. Then
No, that's the point. Like the Hilbert space once you impose these different rules in which the observer's world line must connect the product to the corresponding cat, that just defines a new inner product.
so you're saying
That
that,
defines a new inner product at the non-perturbative level.
so is that the problem of the inner product or the problem of defining the Hilbert space, like the
Well, the inner product, well, Hilbert space is specified by states and an inner product. And if you modify the inner product, you modify the Hilbert space.
okay, yeah.
So the point is that once you modify the inner product at the non-perturbative level using this rule, you get a different Hilbert space.
Okay.
And the dimension of that Hilbert space is over the square, it's not one dimension.
Okay.
It's d squared.
Mhm.
Yeah.
Okay.
Okay, so observables. We studied a bunch of observables, two that I will, the first one I just quickly mention and then I'll focus on the second one, are the two-point function along an observer's world line in this closed universe. And the second one is the center of mass collision energy between a shockwave sent to the left, in the left of a two-sided black hole and an observer falling from the right. So for the first one, let me just say a few words. In the closed universe case, we saw that there is a one-dimensional Hilbert space at the non-perturbative level. So all observables are trivial. They're just multiples of the identity. This means that if you try to compute this two-point function for different times, you always get the same answer of the phase, essentially. What you find with our rules is that this is not true, and in particular, the perturbative answer dominates. So you can study the perturbative two-point function, that would be non-trivial, and that is what is the actual answer that you get with our rules up to corrections which are surprisingly relevant. And we studied this in some detail, let me not go into much detail of that, but it has some pretty interesting properties. For example, you have an accumulation of divergences in the correlator as one point approaches the singularity, which seems to probe in affects the singularity, and it'd be interesting to study whether non-perturbative effects can cure the singularity. So this is something we still didn't do, but it's, I think it has some pretty interesting features. The observable I actually want to focus a little bit more on is this center of mass collision energy. So the setup is that you have a two-sided black hole, you have an observer jumping in from the right side, and you have a shockwave coming in from the left side. Now, what you can do is compute the center of mass collision energy between these two, and that is related and was shown by this paper by Luca and Harry, Maxwell and Levine, Mark Mazzei, Adam Levine. In this paper, they showed that the center of mass collision energy is related to the Casimir of the general representation of the operators that inserted. So the one on the right and the one on the left. So what you can compute is what is the probability distribution of eigenvalues for this Casimir operator, which is essentially the energy of collision between these two. and how that changes with the time where you insert V. So V is inserted in the past, and you can take the time to vary, and you can study how this probability distribution of energy of collision changes as you change the time. So if you compute this at the perturbability level, the diagram we need to compute is something that looks like this. So you have an insertion operator, which represents the observer, and the shock wave, and then you have a projector onto eigenstates of the Casimir. You can do this calculation. You get a probability distribution that looks scary, but it has only two important features. The first one is that this Casimir, at late times, is peaked for the energy is peaked. The peak of this distribution is for energies which are exponential with time. So e to the 2 pi t over beta times is not. That is what the expectation value of the Casimir is. And the other important fact is that there is a 1 over c in front. So if you go at very late times, but not that late, for example, at times which are linear with the black hole entropy, then you get that this probability distribution is suppressed by e to the minus s naught. So it's basically spreading very much, this probability distribution, and becoming very, very small for each value of the Casimir. This suggests that non-perturbable effects, which are also suppressed by e to the minus s naught, could correct this probability distribution leading order.
The suppression is just a normalization, right? I mean, is that right? Am I reading this formula right?
This is normalized.
Yeah, exactly. So, I mean, the point is that the collision energy is like exponentially large, but it's also spread over an exponentially wide range.
Yeah.
Right.
Yeah.
So it's not like it's unlikely that they collide in the first place, it's just that...
No, they collide, but the spread of the energy is very high.
Yeah, so it's not like the probability is somewhat small. Like if I average over the characteristic width of this, if I integrate this over the characteristic width of this Gaussian,
no, I think you get the exact same result. Even if you integrate over some intervals, and you put energy, eigenvalue of the Casimir in bins, large bins,
well,
you will see that.
I'm just saying it's e to the s large, right? If I make e to the s large the bin, then e to the, sorry.
E to the t.
E to the t large.
E to the t large, yeah.
Then probability will integrate over to 1.
Yeah.
Yeah.
But also the wormhole, the correction due to wormholes
will do the same.
will also integrate
Yeah.
order 1.
Yeah.
So in
Yeah.
however large bin you want, the non-perturbative eventually will still dominate. So it's
It's
not
the
a
same
question
one.
about the
That's-
fact that there's many values of the Casimir that you could be in. Even if you define a very rough Casimir, let's say you have 7 buckets that are exponentially large in times, non-perturbative effects still seem to affect the probabilities of that 7 buckets at times or in the page time.
With one definition of the non-typical.
With one definition of the non-perturbative. The one that makes sense in the global.
In the global picture. So essentially, all I'm saying is that you can get a correction to this probability distribution, which is at the same order as the perturbable probability distribution when t is over the s naught. And even if you smear and integrate part of this and the other probability distribution, it will still be the same order. So this tells you that the effective free theory that would be basically this perturbative answer receives corrections over the 1 from the perturbative effects. And this is what I was about to say here. This happens when you consider the old rules. It's a calculation that Luca and friends did last year. That if you want to compute a correction, a perturbable correction, you must include some handle in this graph that we saw before. And it turns out that the dominant contribution, at least with the old rules, is one where the projector threads this wormhole. And you find, in fact, that these kind of corrections are suppressed by e to the minus 2s naught, but they are so independent of c. So of the probability distribution with respect to c is constant and doesn't depend on c. So this is telling you that these effects become important again when the time is linear in s naught. So essentially a deviation. Now, one important fact here is that these contributions arise from correct connections that look like this. So you're taking an observer, you're passing it through the wormhole, avoiding the projector and connect it to the other insertion. So this again suggests that it's a kind of observable that the observer cannot really measure, in the sense that if I want to measure what is the value of the stress of this Casimir on the slice where the observer is, this is not doing that, because we're measuring the Casimir on some slice that does not even include the observer. Now, if you use this proposed modification, what happens is that that kind of contraction of the observer is excluded, and the reason is again that it would connect, it would basically swap between different copies of the system, it does not connect the graph to the corresponding cat. And the kind of corrections that you get are ones in which the observer always crosses the Casimir, the insertion of the projector on the Casimir, I guess.
So just to check, I'm
Yeah.
confusing myself again on this. If you didn't have the projector, we're not doing anything that would make the handle disk dominate over the disk. Right, this is just two-point functions that are separated from large time. There'll be some like ramp thing correlating them, that's zero with your approximations anyway.
I think that is
Go cheaper.
this corresponds to taking this and having a handle that doesn't go over the projector. In that case, it just e to the minus 2 is not suppressed, and it's the same suppression quality.
Yeah, so the point is that this, when you say like even after coarse grading is there, somehow you're not getting the resolution of the identity. Because if the handle disk was really doing a resolution of the identity, then I'm like confused now why summing over the projectors. Right, if you coarse grade, just completely coarse grade. Like,
You mean insert the identity as
okay, if you sum over the disk answer, you should get 1, right? You sum
Yeah, yeah,
all
this
values
is
from
normal, yeah.
Casimir. So somehow, oh, I guess the handle disk answer, the answer point is the phase is changing or something, and so it integrates to 0, but it's like large and you put a modulus on.
You mean the phase of each inner product with a specific value of the Casimir? Yeah, that has a random phase, but in probability it's large. Well, the probability is always positive.
Yeah.
And,
Okay.
So once you include this kind of, when you only include this kind of corrections using our proposal, what you get is that this contribution is suppressed by the same factor of 1 over c that the perturbable answer is suppressed by, and it's also suppressed by a factor of e to the minus 2 star. But some of these actually have these contributions, I deleted here too, but there are much more. The first one in particular increases with time. So this means that if you take time to be exponential, it turns out that this graph becomes of the same order as the perturbative answer. So this is telling you that the corrections from non-perturbative effects to effective field theory come at exponential times in the black hole entropy instead of linear times. Okay, so recap, I guess, just very quickly, we propose these alternate routes for the gravitational path integral if you want to describe an experience of some gravitating observer. And with this new inner product, we find that the non-perturbative Hilbert space is much larger. Particularly, it's non-trivial for a one-dimensional Hilbert space, and the number of degrees of freedom is double for a two-sided black hole. And our prescription also allows to define these observable from an observer's point of view, so only basically only restrict to contractions in which the observer actually crosses the slice on which we're measuring the given observable. And for effective field theory in a closed universe, we found that it's non-trivial and does not break down the leading order in the sense that it doesn't receive large non-perturbable corrections. And for inflating an observer, we also saw that effective field theory is valid until exponential times. I wanted to discuss a couple of feature directions. So the first of all is a generalization to higher dimensions. At least some of these calculations are pretty easy to do, I think, in higher dimensions as well. For example, the dimension of the Hilbert space calculations in arbitrary dimension. It's also interesting to study this, how these non-perturbable corrections for the closed universe could give new answers, maybe some resolution of the singularity as we take one of the points approaching the singularity, as I was mentioning above, for the two-point function. And I think it's also interesting to discuss and understand a little bit better what is the relationship between this construction and something like relational dynamics. So Page-Muller's formalism, CLPW, quantum reference frames, all the stories that try to describe the gravitational system respective to an observer. And I think that our setup should be something like a non-perturbable generalization of these formalisms, but it would be interesting to understand what are the exact relationship. And there are two things that I want to discuss is, first, if there is any lesson that we can learn from holography. From this story, what we learn is that we are basically adding a time-like boundary in the bulk on the world of the observer. So, or if you want, in a more generic setup, you would have a world volume for the observer, and you would have a boundary of the world volume that identifies a time-like boundary in the bulk. So this suggests that maybe that's a place where we could place some holographic theory, and then this holographic theory would know about specific observable stress to this world volume. This would be compatible with the fact that we have a larger Hilbert space, in particular the fact that the Hilbert space is much larger in the black hole case and non-trivial in the closed universe case. And it also agrees with some results about factorization of this Hilbert space that we have in the paper, but I didn't discuss it. And the other thing which I think it would be nice to understand is that if that is the case, then this holographic theory that lives on the world volume, on the boundary of the world volume, could clearly not just be a CFT because it is not an asymptotic boundary, it's some boundary limit to the world. So it could be some form of the foreign CFT, maybe TP bar, I don't know what is the right rule to do that, but I think it's an interesting question to ask. And the other thing I want to say is that this kind of construction does not rely on ADS boundaries. I think this maybe ties back a little bit to the questions that were asked before. This can be done whenever you can specify states in a given spacetime using the gravitational path integral. For example, it can be done in de Sitter. If you want to define a state in de Sitter, I think at least that the most generic way to do it is to take a half sphere, cut off a cup, specify the length and extrinsic curvature of the boundary of the cup, and that defines a state under the equator of the sphere, which would be a state in de Sitter. This is more general than orthologing in the sense that if you take one of these states and it would be backwards in time, it would not be a smooth sphere, but rather it would be a sphere with a defect. Then you can use the same kind of rule to compute overlaps, square of the overlaps, and so on. And you would find that a square of an overlap would have a first correction, which computes again the variance between the inner product of two such states, with, which is given by the connected sphere with 4 folds. So this is also something which is over the e to the minus 2 naught, so it's a very small variance to the overlap, and suggests that the Hilbert space for this global de Sitter would be non-trivial and actually pretty large. Whereas with your rules, you would get something which is one-dimensional as well. And of course, this is for now at the level of pictures. The fact that that's e to the minus 2 naught is just determined by the Euler characteristic of that geometry. But it would be interesting to try to do, and this is something we're starting to do, a precise calculation of this specific model, and then study maybe observables in de Sitter, higher dimensions, and whether this can be generalized to more generic spacetimes, which is, of course, always the goal. Okay, so this is what I have. I leave you with this, which is, I think, very on point. And also, beyond, I feel like, well, we're all observers with the clock after all. It's also a metaphor of how the project went, more or less. Any other questions?
So in higher dimensions, it seems like the details of where you cut the hole or whatever will change the entropy, change the like the suppression in higher dimension doesn't necessarily come from an Euler characteristic, right?
Right.
So it's like, it's a little bit, it's not always gonna be S de Sitter or something, it's gonna be
No,
over there.
Yeah, so it would still be probably something suppressed by e to the 1 over g Newton.
Yeah, no, that part.
The exact integrals, like, even our results for the closed universe are about kinetic gravity, it's exactly to the 2s now times the integral. So, yeah, in general,
In general,
would be something else, which I think still scales with e to the 1 over g Newton.
yeah, that's possible, but related to that, so it's interesting that in the sitter, like in the closed universe, you can sort of see that some of the non-perturbative corrections that you're predicting, or let's say a 2-point function in the sitter, will presumably be like non-filter and curved background plus some exponentially small correction, and it's so sometimes it could be that the exponential small correction is in conflict with the observer's measurement accuracy, but that's because of entropy bounds and stuff like that, right? It has a Lorentzian interpretation why that observer is bounded in entropically, kind of.
Yeah.
But it's not obvious that these two numbers always have to agree. Like the number that comes out of the suppression
could be
could have nothing to do or have very little to do with the bounds that an observer has due to entropy bounds. Or if they are always tied, it's an interesting story. Why?
Okay, on that I agree, except I still suspect that these suppressions are, well, okay, I think that it's plausible, I don't know what exactly, but it's plausible that you can build observables for which these effects may actually become large. If you maybe, I don't know, integrate over a very long time or something like that. If the specific corrections, it's true that these two numbers can be...
But I'm not even sure why these two numbers are always tied together. That's what I'm pointing out. Maybe the number that comes out of the suppression of the, let's say, the last diagram is... Okay, it's a small correction, but the entropy bound, maybe the observer maybe the Lorentzian entropy bounds don't limit the observer as much as enough to exclude them from observing that effect.
Yeah, but I suspect that the model, a realistic model, the point is that you also need to take into account the dimension of the Hilbert space of the observer. Right? Which is sort of that. But you need, if this is e to the minus 1 over g suppressed, then the observer needs to be...
No, but it could be e to the minus 1 over g with a different
coefficient.
Right? So
no,
I suspect at the end of the day it will be limited. But I think, but it would be interesting to find why these two seemingly different numbers are always sort of tied to each other.
Maybe I misunderstood, but for instance, in the case of the center of mass collision energy, we saw that an observer with an apparatus with very few bits of information could see a large deviation from the perturbative results. Right? Because we only put the center of mass collision energy in 7 buckets, so you need very poor accuracy for that in principle. And you could in principle still detect these wormhole results even though your entropy is bounded and much smaller than S0, than the entropy of the black hole.
Yeah, I think what I was referring to is like the specific correction. Say that you have an observable with a small correction, then it could be that the small correction is still accessible to an observer. I think that's what Armin was pointing at. If there is some observable that you can integrate over, say, long times or something like the center of mass collision energy, in that case you have large effects. But I think what Armin was suggesting, there could be cases in which maybe the small corrections are actually not that small, right? But I still think that the observer's Hilbert space must be must scale with e to the 1 over g Newton in order to probe those kind of effects. So yeah, maybe it's technically possible, or maybe the observer needs to be a black hole.
How large is my Hilbert space?
Yeah, that's the point.
No, that was a question.
What, sorry?
How large is my Hilbert space?
In
this one?
what Armin was suggesting is that in the center it's upper bounded by...
No, I didn't really mean that, like for me.
Oh, yeah. Well, it's... It does not scale with e to the 1 over g, I would say.
I would agree with that.
Yeah.
but I just feel like, I'm very skeptical of the idea that the observer can be written into the laws of physics. That doesn't mean that we don't have to take into account the fact that we are encoded inside of the universe.
Well,
You know,
this is-
we're sort of very, even at the level of quantum field theory, like whether or not you think there's an observer there, depends on how you look at the state and what basis you use and so on. I mean, it's very tricky. And in my, like, if I change one electron on the tip of the nose, it's already an orthogonal state. It's not like this line that you define there.
No, I agree in principle with that. The problem is that in quantum gravity you have situations in which if you want to ask questions about one observable measured by an observer, which is what we're ultimately, I think, interested in. What is the value, predict what is your own experience. The problem is that in quantum gravity you can have situations in which if you include non-perturbative effects, the notion itself of the observer is not even well defined.
My point is that it's already not well defined at a much more primitive level.
Sorry, but in the example that you gave with your electron, switching a spin and leading to an orthogonal state,
Yeah.
that U or some linear combination of some states, right? And changing the coefficients of those are the delta i's that Stefano described, and changing the spin in the electron on your nose changes the coefficient Ci in such a way that you're creating a state that's orthogonal to your state right now, right?
Right.
And that's accounted for. That's
No, because you have no way of deciding whether the electron belongs to me or to the environment, and frankly, it doesn't matter, right? And the same as when, I mean, there's some,
but
I'm not an isolated system, first of all. This observer is treated as a sort of unique isolated system that's singled out in the theory. And that's just wrong at the level of quantum field theory and a fixed backgrounds. Even at a much more primitive level than these non-perturbative quantum gravity calculations that we're worried about here, I just feel like it doesn't remotely capture what an observer is and how we would like to cover our own experiences. And
because of the lack of
because
interaction,
we are a
you have
subsystem of an
these-
extremely complicated system. We're very temporary, we fluctuate in and out.
Yeah, and all these
We're entangled with the
effects.
rest of the world very strongly.
Yeah, that's why these states can be entangled with the rest of the universe, right? But
And
specific
to the
states
extent that we
that
said we
were.
observed something like this or that happen, it's always because we lost information, there's entanglement, we lose information in the environment. Like, I don't understand how this model captures that. Like, it feels to me much more like we're treating the observer like an external system that we've added to the universe. And it's very important that we keep track on what that very special system is, because it enters all the rules that we have for the physics that we're supposed to calculate. Like, it enters the laws of physics. Like, that special system enters the laws of physics.
No, it enters it. If you want to ask what happens along the world line of the specific observer, yes, it enters the laws in that sense. But
Maybe in other words, it doesn't enter the laws of physics, it enters the definition of the states. And I think that is true also in quantum theory. You cannot say what is an observer measuring.
But you have to start by identifying an observer, and then you build your laws of physics on top of that. I think that's what's bothering me.
But I think that's fine, right? Like, if we're gonna be asking questions using some experimental apparatus, I think it's fine to say, like, okay, if I'm using this experimental apparatus to ask these questions, like, I should be making that experimental apparatus a part of my space-time. It should be interacting, and we're saying these may be the rules for how we
Yeah, you
interact.
can ask about that. But you don't ask about that first, then say, now let me go to these different laws of physics in which the gravitational path integral is substantially modified compared to the usual laws. Right? It's just like, I don't know, anthropic selection or something, right? We're not surprised we don't find ourselves in interstellar space because, of course, that's not where the observers are. That's fine, but we didn't use different laws of physics to first compute how the universe evolved.
But I think you're already using a different, you can I think to compute observables where you ask questions from the point of view of this observer. So how is that a modification? I wouldn't call that a modification of the laws of physics.
I think the idea is that the anthropic selection in some way leads to these rules. for the gravitational path.
Yeah.
That I don't,
Exactly how is
I don't see that at all, because it's like a really substantial modification of the laws of, how you should evaluate compute the gravitational path as well.
I mean, in some way, if you're you imagine this observer is doing more complex interactions, and then you're conditioning on those interactions, like.
I don't, then there should be a way of like doing the calculation using the usual rules and afterwards to say, okay, now let me focus on this or that. And then it should come out of that. But that, I don't think that's what's happening.
Is the claim that's meant to be possible or not? Or don't know?
That what? That it's
But
not.
there should be some way to use the usual rules, but then like consider observables that are conditioned in some way, or like ask certain questions within the usual rules that end up in these species.
I think at the level, we had a comment about this, which at the level of the, if you want to consider a matrix interpretation of this, these rules are essentially equivalent to computing whatever you want and averaging over the matrix associated with observer expression. So you can use those rules and then do an average over the matrix only. Isn't that sort of what you're talking about? So that you have a matrix model describing matter, a matrix model describing the observer, just a different matrix, and then a matrix model for GT, and then you just average over the matrix of the observer. I think that would recover our rules from it.
It sounds like you kind of want like a controlled approximation, like some parameter that you can dial, where in some limit you get these rules and in another limit you have.
I don't want anything. I'm not getting involved.
But one thing practically, isn't it quite damaging for a proposal that it doesn't even make sense if the observer is not some saddle point approximation? That seems weird, right? Like, for example, you can imagine an observer that the wave packet that measures something as it crosses the horizon, they completely delocalized after that.
Yeah, it's not, here it's not about what happens to the observer after they collide with the particle.
Yeah, but I'm saying in
It's
this
about,
rule, they're
predicting what-
on the side, right? You can't really.
Well, they would have just
But
been Keldysh.
Huh?
Like the Lorentzian analog of this is some Schwinger Keldysh thing, right? It's the graph
Right.
reaching the cats. So they die, but then they come back to life in the graph.
Yeah, I thought this
Yeah,
was
But
supposed to be
can you
continuous.
decide,
Here we're just
well,
comparing
I'm just
the-
saying, you're sort of, you're ruling out some things, right? You're saying this diagram, no.
Yeah.
You're saying that the rule for excluding seems to be tied to a line connecting to the field.
Well, if you want, it's more tied to a weak contraction between the operator
But
and
it's
certain
binary, right?
Huh?
It's binary. It's like either.
It's yes
Yes
or
or
no,
no.
you either include it or you don't, right?
Yes.
So, but if it's a wave, I suppose it's a wave.
But what's bad with that?
Because
There's
I think in the real world, you're not gonna get sharp criteria like that for like deciding whether to include it or not.
Right, like that picture is gonna have like all kinds of, the last picture is gonna, there's not gonna be like this versus that or whatever. It's not gonna organize itself into a set of different,
You're saying that there will be
It's
more
just gonna be some-
contributions.
it's just gonna be some like, you have to do like the full path integral of the particle.
Yeah, I think the point is that those, it depends what probability you want to ask about. And when you work with the global rules, that does compute the probability of transition between two states. It's not necessary that that's the probability of transition that the observer sees when they go to a certain height state.
I'm saying,
Observable.
let's try to implement your rule.
Yes,
But not assume that the points that you're inserting on the asymptotic boundary that you want to call observer, that their inner products are computed by Saturn. That there's no word line associated with them. They're just some like wave packets that could be localized. That's just, can you define your
Even more
rule?
strongly, right, there's some approximate subsystem of a quantum field theory state that's evolving together with the gravitational state. It's very hard to define exactly what that observer is, right? And within that messy situation, you can still write down these rules.
I think these rules are an approximation. So they're an approximation that's valid when the proper time along the world line of the observer is parametrically small. Sorry, his order one is not parametrically large. For instance, if you're in the sitter and look at an observer for a time that's exponentially large, of course you should worry that the observer goes in and out of existence
I
and
even
so on and so
about
forth.
something, but suppose the observer was a wave packet having nothing to do with the sitter time is allowed. They just be localized after, I don't know, 20 seconds, but they could still do measurements in the first 10 seconds. Like, just an observer is not necessarily something that...
Yeah, you're worried about the world line approximation,
Yeah.
right? And I think there is a way to deal with these, whether or not you impose these contractions, whether or not you include these contractions or not, even if you prepare a wave packet. It's again, if it's a question about which weak contractions between operators in a weakly interacting theory include, that doesn't have to do with which world lines you're allowed to allow weak
interacting is important? Like, so you need some rule to have this...
Probably in order to define an observer, right?
But I mean, that's a very fundamental thing to say, right? Like, if you say that an observer only makes sense when you have this, like, either word line or big contractions.
If you, I don't know, I don't live in a very strongly interacting world, right?
I think this would make sense as an approximation after you've already played. The problem is that you seem to be defining new laws for the gravitational path integral, which is like at an incredibly fundamental level, you're trying to rewrite the laws of physics. And for that, you need something better than to say that it's based on an approximation.
There's
Because, you know, the rules should make sense, but even if I have to use approximations to evaluate them only approximately, there should first be like some clear statement of what the rules are that I'm then approximating. That's what I meant by the observer entering the laws of physics. That sounds really dangerous to me because the observer is just such an incredibly fuzzy concept.
Okay, a measurement made along the world line is not a fuzzy concept, right?
It is, actually. Even that is a fuzzy concept.
Why?
Well, because again, even in quantum field theory, if I don't allow you to sort of go in from the outside and act with operators, but I just treat it as a closed system, I generally have superpositions. I have some fixed state that's just evolving. I can think of it as superpositions. I can choose to trace over some subsystem in which I will have a story in which an observer makes a measurement like that, but I'm not forced to, and it's very much just a subjective thing to do. And this is like something that actually describes the real world. Like if I give you the state of the galaxy and that's all I give you, you have no way of telling where we even are because we've probably, already like diffused over like some enormously large scale in the last 6 billion years. And so those stories are stories we tell ourselves, from a very limited perspective that we're in, but that they sort of completely fall apart as soon as I go to a slightly larger scale and more fundamental scale, before I even include gravity.
The only thing I meant is that, we do make an approximation that we do, even in quantum field theory, that we make measurements along some specified world line, right? We have a very heavy experiment, and, we perform scattering experiments within that setup and make concrete measurements, right? And that can be viewed as measuring the scattering amplitude along the world volume of the experiment that along the experimental apparatus.
What I'm saying is we wouldn't have any way of recovering this even from quantum field theory.
No, but we do.
Unitary global treatment without tracing over some environment, choosing a particular outcome in various previous instances, so that we can say, oh, we're actually this world line, and now we've made this measurement, and this was the new outcome. It's the result of some incredibly long, non-fundamental sequence of subjective choices that even got us to the point where we're asking the question.
I understand. My only point is that we can make predictions for the measurements that we see along the world line in an approximation where, either the observer is static or even the observer is not even there in quantum field theory, right? We predict what scattering amplitudes are, right? And we don't we don't consider states in which we put the LHC as part of the state, right?
Well, when we compute scattering amplitudes, we compute them at infinity of some idealized.
Can I make a point about this? Like, So if I were just gonna do, like let's forget gravity, if I were just gonna do E&M, I could do it with like asymptotic states that are not actually eigenstates in my Hamiltonian, and they really will, like it's not just, they're just not well-defined concepts in the theory. But I could also do E&M by doing, the regular Lagrangian plus a point charge. And there, that point charge is really a thing that I can talk about at any time slice, because it's in there. And I feel like what we're doing here is pretty analogous to saying, like, okay, well, we know how to do this perturbatively, and it's very unclear what the rules for that point charge should be non-perturbatively. And we kind of assume that it gets treated the same as everything else, but what if that's not the case? If that's not the case, actually a lot of things end up getting better. So I feel like this is maybe, like I agree with you that if I don't put that thing into my Lagrangian, it is not a well-defined concept. Like gravity on its own does not have observers that behave like this. But I think, the thing that I was saying before with the experiment is about saying, like, I want to put my experiment into the system because it is this special thing that I'm using to perform my measurements. And my experiments are not relevant in the world where the LHC has dissolved. Right? Like, that's just not the thing that I'm going to end up measuring. So let me put it in there explicitly.
So maybe on the same page is like saying that we said it's a specific number of choices that leads to the idea that you have some observer. You need to trace out of the environment, that depends on what are your degrees of freedom and so on. What we're proposing this is a way to model those choices and give you the corresponding system with respect to which you want to ask questions.
Maybe an encouraging thing is that the results are largely independent from the from the properties of the Hilbert space of the observer. So I think
But the results are a little bit like, maybe this is oversimplifying it, but it's a little like, okay, if I neglect some tiny detail about Hawking radiation, and it looks like I can recover Hawking's result, right? So it's very easy, in other words, to lose, the detailed information that allows you to see unitarity. Similarly, I'm not surprised that it's pretty easy and universal to lose the detailed information that, the miracle was when the gravitational path integral gave you one state for the closed universe. It's when it gave you the page curve. You have to be really careful and keep track of everything to do that. It's not extremely shocking to me that if you modify this in one way or another and mess with it in one way or another, there's a pretty universal outcome, which is you just go back to quantum field theory on a phase background.
But that's not the outcome. That's not the outcome.
Right, so this is somewhere in between.
Yeah.
But it's not.
It's still, I think the surprising thing is that it's a
from
well-defined Hilbert space.
Yeah, and also that I think it recovers quantum field theory in a spacetime in a specific limit, and it gives non-trivial corrections to it, which don't break it.
But the
I think
corrections,
that is not trivial.
the corrections you're talking about, you mean corrections of e to the minus s naught, right? E to the minus 2 s naught. That's not something, there's no analog of that for an observer's world line in higher dimensions. Right, like that's the sum of it's the area surrounding the observer, which in high dimensions just goes to 0 if you take the observer to be a world line. So in high dimensions you can have essentially no cost to making the observer do all sorts of weird things, and it's really just a world line. It's just in 2D that there's a topological area surrounding it.
So in a higher dimensional, more random model, you would have some more volume of the observer, I assume. And then area would not be. So
Okay, then it would be the area of that world volume.
That's so enormously poorly defined, right? Like, what is that for me? Like, and the size of the corrections depends exponentially on something that is so random. Like, can I be miniaturized a little? I mean, can I be an elephant? Does it matter? It can't possibly be the surface area of my skin, right?
So the size of the correction don't depend on you.
I thought it depended on the.
No, like the answers that we get for, say, the size of the Hilbert space don't depend on the observer subsystem.
They depend, in effect, they're the area surrounding the surface surrounding the observer. It's just in 2D, then that is basically constant.
And just one is that the S naught is equal for G, where
Two
A
I
is
guess it's 2 times the area on either side.
I don't think that that's the generalization in higher dimensions, but
What is it then?
I don't know. Yeah. It's just
That is, it's the cost of creating a wormhole that sucks out the observer's world line, which is roughly the area surrounding the observer. Like, it's like the cost of cutting off a black hole, it's like the area of its horizon.
So you don't expect that, for example, the sitter would be the area of the cosmic horizon?
It's a local thing, Just make a local little wormhole loop. observer goes off to and like dodges, like, yeah, they see something very weird, basically. I didn't see how cosmology is getting involved in this at all.
The relevant parameter to replace
I mean, there is no
But it's the wormhole, the correction that's relevant to them is the wormhole where the observer doesn't go through it. Right, the observer
Where's the
stays
wormhole?
outside, the observer stays outside and some connection
It's
between
just
them.
That way.
observer going somewhere different to the matter, right? Like,
But I thought sort of like because.
what's outside, what's inside, seems, maybe I'm missing something, but it seems not a decision.
I don't know why they got really thought and considered would be considered.
I would have thought two dozen, but maybe we can discuss exactly what you mean.
Like, what would you say the analog of S0 is in high energy?
I think it depends on the setup. I would have hoped that it's for the example of a two-sided black hole.
Bang crunch cosmology plays universe person single side.
I don't see how it could be anything other than what's presses topological fluctuations.
But that geometry with the topology, with the wormhole, could exist even without any worm observer, right? It's
Yeah,
just-
the
it's just-
observer's got the correct.
The observer is just gonna like sort of stay away from the wormhole in a way, right? Like that geometry by itself exists and the observer,
Like,
how is it, how is?
We don't get to contract things when the observer goes into a wormhole on one end and not on the other. I mean, isn't that the analogy?
Yes.
Yeah, so it's contributions whether our wormholes big enough to contain the observer, where your new rules make a difference.
yeah. So you swap the rest of the space-time, but the observer goes through a little wormhole and so it doesn't get swapped. Right, what's the cost of that? It's how big the wormhole surrounding the observer needs to be, but that's like,
Sorry, I'm not sure. You're saying that if I construct the space-time with 4 asymptotic boundaries,
yeah.
right? And ask what the action of the leading connected contribution is.
Yeah,
You're saying that
I'm
that
saying
one
it'll be
is
like
the same.
swap everything,
That
right? Swap everything would have no cost, except it's just excluded by your
Yes,
rules.
yes,
If the
yes,
observers don't go to the right
yes.
place, then make tiny little wormholes for the observers to go through.
tiny little wormhole.
Just have some little configuration they can go through.
You're saying that you could find an on-shell configuration where the action is the same as the sum of actions of 2 individual wormholes, right? That the extra wormhole that you have, a small wormhole that the observer goes through, is has 0 cost in the action.
Yeah. You know, the cost will scale with this size.
With you mean the size of the observer?
The size of a cross-sectional area surrounding the observer to make it big enough for the observer. I mean, it's not very well posed, but
I think that's the issue. The sensitivity to the size of the observer is significant.
Well, I don't know. I haven't done the
If I
calculation.
chop my legs off, it will make a big difference.
I mean, I guess I'm not sure if there's an on-shelf configuration that differs for every different size of the observer, as opposed to saying that there's one connected geometry that lets this work. Like, I just don't know, but it's not obvious to me that the thing that really changes is where you connect, the world line, and then once you've decided that, there is one on-shelf. There's one sound.
on-shell versus off-shell seems like a minor red herring to me. Like there's plenty of off-shell.
Maybe I should say that like the thing that matters is not actually the size of the observer, but that once you've chosen a connection of this line from one point to another, you have a contribution associated with that. Off-shell doesn't matter. You have an answer associated with that connection. Like, is that an obvious thing to
Just
be
think
able
of
to
a random
differentiate?
tensor network that's like almost closed, right? Then if your rules say that the observer is some matter leg and you're forcing that to get glued to the corresponding matter leg and not get swapped. But you can swap everything else and just you just have some cost of whatever the smallest thing surrounding the thing you're not allowed to swap is.
Sorry, and what's the problem with modeling the tensor network in 2D? For 2D
Yes,
answer,
you can do that, and
Yeah.
it's just that you get exactly your thing. But in higher D, you get the point is in 2D it's a 1D network, and so sort of the
all the legs at S
1D
naught.
there plus 1D object has some like finite cost. In higher dimensions, then if there's a more fine grained you make the tensor network, the smaller the cost will be.
But I have to think about it in higher dimensions.
I think even in 1+1D, you could maybe generalize it by going away from the JT. You know, like the fact that all the areas are exactly the same is limiting. You don't need to have the theory of 1+1 if that's the case.
I think you could do it in the general theory of dilettante gravity. Your problem is that the cosmological constant is constant, that the curvature is constant given by the.
Yeah, I mean, the only challenge I think to bridge here, or the minimum challenge one would need to bridge is to have the area, to allow the areas to be not fixed. So that in itself doesn't mean that you have to go beyond 1+1, though I think there are many other issues that are easier to discuss when you go beyond 1+1.
Okay, I think, for instance, if you do it in a general theory of dilettante gravity, where the areas are allowed to vary, you would get the same result.
Yeah, and then you might be able to capture the sensitivity to the size of the observer. Because if you stop, I mean, you'd also have to stop modeling the observer as a whole. I mean, the observer would have to enter. Yeah, it's a little harder than 1+1. Because the observer here is by definition has the same size as the. I guess we're giving them the size of the dilettante value that they're living on.
If you like fixed the dilettante profile and you did it more precisely, you'd find that the exact correction is like e⁻² the dilettante value of the observer, rather than the dilettante value of the horizon or anywhere else. That's because it would just reduce to like a fixed area state tensor network style computation.
Sorry, are you
That's
saying
some
even in
finite-
JT? Or-
Yeah, I mean, you're a leading order, that's just S naught, right?
But we accounted for the subleading
Yeah, and
contributions in S naught, like our result, the log of the dimension of the entropy is 2S naught plus the log of this integral. That's determined by the density of states. And I don't think that, at least I don't think off the top of my head that that's given by the value of the dilettante on the world line of the observer, the minimal value of the dilettante.
so when you say the log of the density of states?
The log of the integral of the density of states, I think.
This number d squared.
Yeah, sorry. So the point is that I think that the dilettante can just get arbitrarily large. You're not in you haven't fixed the value of the dilettante, so there's just a full integral.
Yeah, so here what we were imagining is that the set of states that we're preparing project to some, you project the energy to some
I'm saying
finite
that
interval.
can be written as an integral over superselection sectors associated with different observer dilettante values, and for each observer dilettante value you get like e to the I guess you have the dilettante value one side and the dilettante value the other side, and that's why.
It is the dilettante values on
on each side.
on each side of the observer, but not on the
But that's
world
the
line.
area of.
Yes,
So you're replacing
that's
S naught with
it's
phi
allowed
naught.
to be distant.
So you're replacing S naught with phi naught, and is this what you're doing? Just to clarify.
Yeah, I'm saying that. I mean, that's why you get the integral
Yeah,
over
I just wanted
S where not S. Is the it's the area surrounding the observer. Or e to the area surrounding the observer integrating over that area. But in higher D, like the area surrounding the observer just comes down to how close you can make it to the observer. Yeah. That's what I feel set for your legs now.
think the hierarchy computation, well, I'm not sure about it. The only situation that I thought a bit more about that's more akin to this computation is the case in which you consider spherically symmetric shallows as your observers, as an example, in which case it's not true that you could make the area arbitrarily small.
I think in that case I would expect that the answer you get is actually independent on the size of the shell. I thought you would get something which is probably e to the 2s power.
So, it's harder T.
That's right, now we're gonna get to the convertible part.
The size of the thing is always e to the s observer, which makes
That's not the size of the Hilbert space.
Well, no, sorry, okay, sorry, that's what they said.
Yeah, what they actually compute, if you look at their computation, is the entanglement entropy between the observer and the subsystem. And
Should I turn it off? I don't know.